Welcome to our math lesson on equations of lines and planes. In this video, we'll explore the different ways to represent lines in two-dimensional space, lines in three-dimensional space, and planes in three-dimensional space. Let's start by understanding how we can mathematically describe these fundamental geometric objects. Let's begin with lines in two dimensions, or the plane superscript 2. The first representation we'll discuss is the vector form, also known as the parametric form. In this form, we describe a line using a starting point and a direction. Specifically, we write r of t equals r subscript 0 plus t times vector v. Here, r subscript 0 represents a point on the line with coordinates x subscript 0 and y subscript 0. V is a direction vector with components v subscript x and v subscript y, and t is a real parameter that can take any value. Let's look at an example to make this clearer. Suppose we want to find the equation of a line that passes through the point 1, 2, and has a direction vector of 3, minus 1. We substitute these values into our parametric form. R of t equals 1, 2, plus t times 3, minus 1. Writing this in component form, we get x equals 1 plus 3t and y equals 2 minus t. As t varies, the point r of t traces out our line. For example, when t equals 0, we get the point 1, 2. When t equals 1, we get 4, 1. And when t equals minus 1, we get minus 2, 3. Next, let's derive the symmetric form of a line equation. From the parametric form, we have x equals x subscript 0 plus v subscript x times t, and y equals y subscript 0 plus v subscript y times t. To eliminate the parameter t, we can solve for it from both equations. T equals x minus x subscript 0 divided by v subscript x, and t equals y minus y subscript 0 divided by v subscript y. Since these expressions for t must be equal, we get x minus x subscript 0 divided by v subscript x equals y minus y subscript 0 divided by v subscript y. This is the symmetric form of the line equation. Using our previous example of a line through 1, 2 with direction 3, minus 1, we can write the symmetric form as x minus 1 divided by 3 equals y minus 2 divided by negative 1. Both the parametric and symmetric forms represent the same line, but the symmetric form eliminates the parameter t. A common scenario is when we want to find the equation of a line passing through two given points. Let's say we have two distinct points, x subscript 1, y subscript 1, and x subscript 2, y subscript 2. First, we can compute the direction vector v as the difference between these points. V equals x subscript 2 minus x subscript 1, y subscript 2 minus y subscript 1. Then, we substitute this direction vector into the symmetric form using the first point as our reference point, x minus x subscript 1 divided by x subscript 2 minus x subscript 1 equals y minus y subscript 1 divided by y subscript 2 minus y subscript 1. For example, the line through points 1, 3, and 4, 7 would have the equation x minus 1 divided by 4 minus 1 equals y minus 3 divided by 7 minus 3, which simplifies to x minus 1 divided by 3 equals y minus 3 divided by 4. Now let's move to three-dimensional space and explore lines in superscript 3. The vector or parametric form for a line in 3 dimensions is very similar to the two-dimensional case. We write r of t equals r subscript 0 plus t times vector v. But now, r subscript 0 represents a point, x subscript 0, y subscript 0, z subscript 0, and v is a direction vector, v subscript x, v subscript y, v subscript z. In component form, we have three equations x equals x subscript 0 plus v subscript x times t, y equals y subscript 0 plus v subscript y times t, and z equals z subscript 0 plus v subscript z times t. Similar to the two-dimensional case, we can derive a symmetric form for lines in 3 dimensions. If all components of the direction vector are non-zero, then we can write x minus x subscript 0 divided by v subscript x equals y minus y subscript 0 divided by v subscript y equals z minus c subscript 0 divided by v subscript z. This form is particularly useful when we want to eliminate the parameter t from our equations. However, if any component of the direction vector is 0, the corresponding fraction is undefined, and we would need to use a different approach. Now, let's move on to planes in three-dimensional space. A plane in superscript 3 is uniquely determined by a point on the plane and a normal vector, which is perpendicular to the plane. Let's start with the point normal form. Given a point p subscript 0 with coordinates x subscript 0, y subscript 0, z subscript 0, and a normal vector n with components a, b, c, the equation of the plane is the dot product of n with the vector from p subscript 0 to any point x, y, z on the plane, which equals 0. Expanding this, we get a times x minus x subscript 0 plus b times y minus y subscript 0 plus c times z minus c subscript 0 equals 0. Let's work through an example to make this clearer. Suppose we want to find the equation of a plane that passes through the point 1, 0, 2 and has a normal vector 2, minus 1, 3. Substituting into the point normal form, we get 2 times x minus 1 plus minus 1 times y minus 0 plus 3 times z minus 2 equals 0. Expanding, we have 2x minus 2 minus y plus 3z minus 6 equals 0, which simplifies to 2x minus y plus 3z minus 8 equals 0. The point normal form can be rewritten in a more general form. The general or scalar form of a plane equation is ax plus by plus cz plus d equals 0, where a, b, c is the normal vector and d is a constant. To find d, we use the fact that the plane contains a specific point, x subscript 0, y subscript 0, z subscript 0. Substituting this point into the equation, we get a times x subscript 0 plus b times y subscript 0 plus c times z subscript 0 plus d equals 0. Solving for d, d equals negative a times x subscript 0 plus b times y subscript 0 plus c times z subscript 0. Finally, let's look at the intercepts form of a plane equation. If a plane intersects the 3 coordinate axes at points a0, 0, 0, b0, and 0, 0, c, where none of a, b, or c is 0, then the equation of the plane can be written as x divided by a plus y divided by b plus c divided by c equals 1. This form is particularly useful when we know the intercepts of the plane with the coordinate axes. Let's summarize the different forms of equations we've covered. For lines in both superscript 2 and superscript 3, we have the parametric form. Our equals are subscript 0 plus t times v. The symmetric form, x minus x subscript 0 divided by v subscript x equals y minus y subscript 0 divided by v subscript y. And in 3 dimensions, equals z minus c subscript 0 divided by v subscript z. For planes in superscript 3, we have the point normal form, a times x minus x subscript 0 plus b times y minus y subscript 0 plus c times z minus c subscript 0 equals 0. The general form, ax plus by plus cz plus d equals 0. The intercepts form x divided by a plus y divided by b plus c divided by c equals 1. Each form has its advantages, and the choice depends on the given information and the specific problem you're solving.